Hey, Michael, Connor, can you hear me?
Yes.
Thank you. Uh, let's wait for a minute or two to have more people come in. All right, one more, great. Okay, let me start the lecture. It won't be very long. I just want to go through the final design project for this course. I got a number of emails telling me they cannot make it. I will record this and put on Blackboard so other people can see this later. It's coming to the end of the lecture, to the course. I just wanted to use a final exercise problem for you to just pull everything together. You know, the main things is the code you developed and use that to design something with some application background. So this is basically the problem. So let me get up here. All right. So I want you to design a pressure vessel. That has certain size. The ID is 0.8 meter and OD is 1.8 meter. The vessel is to be pressurized up to 10 bar. You can figure out what kind of Pascal. About 1 bar is roughly 10 to the power 5, 100,000 Pascal. That's 1 bar. Okay. So you can multiply 10, that's 10 bar. It's a gauge pressure. It's the difference between inside and outside. That's gauge. So basically inside pressure is 10, if outside pressure is 1 bar, the inside pressure will be 11 bar. The difference is 10 bar. The difference matters. That's what you use to calculate the stress. So you would use the pressure vessel equation to calculate the load in the hoop direction, the actual direction, and that will be the load to the wall. So I want to design the cylindrical wall of the vessel, ignore the ends. The ends are more complicated. Now you don't have the tool. We don't have the tool to do the full-blown analysis on that. You need a finite element analysis. So we want to ignore the end of the pressure. We'll just design the cylindrical part of the pressure, the wall, cylindrical wall without the end. We also ignore the end effects and mass of the ends. So we don't design the ends. Now I want you to use a factor of 1.9 in your strength calculation. So if you calculate, if this is a design, you calculate a failure stress, that should be 1.9 times the stress causing failure. So there is some factor safety programmed in. That factor safety is 1.9. I want to use this number. Okay. So the first part of the question is really a very simple design. I want you to first design a steel pressure vessel. This is your control cases. You want to later on compare your composite one to this one. These are assumptions I want you to make. The typical steel, this is a real steel properties. These are kind of not very high strength, mid low strength steel. Typical low cost steel would have this kind of properties. The 200 gigapascal stiffness, yield strength is 350 megapascal, Poisson ratio 0.3, and density of 7.8 gram per cubic centimeter. So I want you to calculate the thickness of the cylinder. You would use failure criteria for metals, maximum shear stress or distortion energy, things like that, to figure out what kind of thickness wall is necessary to sustain 10 bar differential pressure without yielding. Once you figure that out, I want you to calculate the axial and diameter expansion. Basically, once you put 10 bar pressure in the vessel, how big does it grow in axial direction and in diameter direction? Okay. Again, I want you to ignore the end effect. So you would have some idea as a controlled conventional vessel. If you build out a steel, this is the weight you're looking at. This is how much it deform. Okay. This is not so hard. Don't think there's too much of this. This is basically equivalent to a homework problem for EMCH 260. It's not very difficult. If you review the stuff you learned before, you can easily figure this out by applying whatever you learned in solids or junior design. So that's not the main part of the project. The main part of your project is part 2. Okay, that's what I want you to do using your CLT code. So far, any question on the part 1? Anything that's not clear? All right, part 2 is a real work that I want you to try. I want you to try to design the same pressure vessel with carbon epoxy, graphite epoxy, lamina as a building material. So you basically, it's the same requirement, the dimension, the pressure differential, ignore the ends, things like that. Use the graphite epoxy property from this table, which I've used before. The last column is the graphite epoxy property. This have you all the elastic property plus the strength plus thermal expansion. Okay. And use that as your base property when you design. Okay. You would need these all the E's. For your CLT, you also need all the strengths to apply Sai-Wu criteria. You only need those numbers. Okay. All right. I want you to assume the pressure vessel operates at room temperature, and the stress-free temperature is 350 Kelvin. This is for thermal stress calculation. You assume at 350 Kelvin, it's a thermal equilibrium, no thermal stress. So since you operate at room temperature, let me put on here. Room temperature, assume is 20 degrees C. There will be differentials. So you're gonna have a thermal stress in combination with your 10 bar pressure loading. So there will be 2 stresses applied: thermal stress plus your mechanical stress due to 10 bar differential pressure. Okay. Again, I want you to ignore the end effect. So the first thing you want to do is design the layout of the laminate. These are the wall of the pressure vessel. I ask you only use these directions. Don't use like 57, 32. Only use this 6 direction. You don't have to use them all, but if you use any layout, any laminate, use these directions. These are measured with respect to the actual direction of the vessel. Okay. So 0 will be along the axis of the vessel. 90 will be the hoop direction. Okay. 45 is the diagonal direction or things like that. So you want to use this only these lamina, only these directions. Okay. Assume the lamina thickness of basically 1/8 millimeter. So if you use 8 lamina, it will be 1 millimeter thick. Okay. And you build up a thickness using these layers. What lamina you want to use and how do you build up is your choice. Now, when you make your choice, remember the design rules that we had gone over last lecture. So those are things you want to apply. And then use Sai-Wu failure criteria for strength calculation. Obviously, the number 1 requirement for this pressure vessel is that when you apply 10 bar, it will not blow up. So the thing will not fail. And you want to use Sai-Wu failure criterion to figure out how safe it is. Okay. All right. I want you to calculate, once you figure out the design, the layout, I want you to calculate the total mass. You want to figure out how many layers, how many laminate you need, how thick laminate, and then estimate the mass of the vessel. Assume the graphite epoxy is 2.3 gram per cubic centimeter. So it's quite a bit lighter than steel. Steel is 7.8 and this is 2.3. So once you determine the number of lamina you need in laminate, you calculate total volume and you can calculate the mass. Okay. Also, I want to calculate the axial and diameter expansion of the vessel when 10 bar gauge pressure is applied. Okay. And this is basically came out of your CLT code. You're gonna use CLT code to calculate the membrane strain. The membrane strain will tell you how much it grows in the actual direction and the diameter direction. Okay. Any questions? So the number layer and then how you sequence them, how do you combine them is how you're in your design space. You're gonna make that choice. Okay. And the main design tool you need to solve the second part problem, which is a lot more, much more difficult than part one, is open-ended. There's no single correct solution. Depending on your choice, the layout, the sequence, there could be multiple correct solutions. The layout is basically your choice. You want to select a layout that is efficient, in that it's safe under the pressure. At the same time, it's light, use less material. Let's say you design a layout of its factor safety 2. One people used 32 layers, the other people used 16 layers. Achieve the same goal, same factor safety. That 16 layers will be more efficient in the sense that it's lower cost. The material is more efficient at carrying the load. Okay. If you less material, it'll automatically be lighter too. So you may want to compare a few layups. You don't want to be. I don't need you to write optimization code to exhaustively pick the optimal layup. I don't need you to do that. I wanted to compare maybe a couple, 2 or 3 different layup that you brainstorm out. You think you may think I should use plus or minus 45 on the inner outer surface. Then I need to apply the material that actually resists the most the actual, and then hoop direction next, and that'll be 090s, and then I would put plus or minus 16 in the middle, things like that. That's good sort. And then you just try few different layups, and you do a calculation and see which one is more efficient. Okay. Each layup has to be built thick enough to resist the 10 bar pressure. So under 10 bar pressure, you would have a laminate failure threshold above 10 bar. Okay, that's a given. Each laminate you put together has to be strong enough. Okay, with a factor safety 1.9. Okay. All right. So in the end, I want you to basically write up your analysis. Focus on second part, obviously. First part, usually, if you reasonably go to solid, you can knock this out half a page. It's pretty simple. The second part may take more than half a page, may take a few pages. And then you want to back up with your calculations. I want you to prepare a design report with all the analysis. If you use put some explanation to it, use it with diagrams, equations, calculations. Then I want to summarize the result in the table, maybe several tables. You want to compare your design number 1, which is steel vessel, and then your composite vessel design number 1, number 2, number 3, and then draw some conclusions. What is the final layup? And how do they compare in terms of mass, deformation, cost, in terms of material volume, things like that. I want you to finish this in December 6th, which is happen to be the date for the final exam for this course. We're not gonna have a final exam. This is our final exam, by the way. So that I want you to finish that, and by December 6th, before the end of the day, I want you to email me, email your report to me. Email your report to, okay, PDF format 1. And this is the table that you need to calculate. Is this clear? Connor, Evelyn, Michael, questions? It is Michael. It is in-plane loading. You don't consider it out-of-plane loading. So basically, when you have a thin wall pressure vessel, the main loading, if you recall solids, is the actual stress and hoop stress. You would figure out the NX and NY. So the pressure will basically result in NX and NY. That's the main loading. The pressure transverse to the wall is very small compared to your NX and Y. When you calculate, you figure that out. Okay. So you basically analyze this problem similar to a flat plate with a biaxial tension. Actually, the tension in the hoop direction is higher than the tension in the actual direction. Okay, and that you can figure out with the basic solid equations. All right. Any other questions? Look like Evelyn's gone. Any other things you want to clarify? You basically ask questions for other of your classmates. If they were here, they would have a question maybe.
I think I'm all set. Thank you.
Okay, Evelyn's back. Michael, any more questions?
No, I can't think of any more right now.
Evelyn, is this all clear? Sounds clear to you?
I'm good for now too.
Okay, great. Let me see. Let me add one thing here. 0 is the actual direction. 0 is the actual direction. All right, it's very easy to forget conditions. I'm sure there will be some forgot. Whenever, when you read this, when you try to do this, if any questions, email me, let me know. I will upload this right now to the Blackboard. Well, Connor, Michael, Evelyn, I really appreciate you guys show up here. I would just finish the remaining editing of this and I will post on Blackboard. Okay, if no more question, I'm gonna stop here. I will let you work on your stuff. I know you got very busy by the end of the semester. All right, I'll looking forward to seeing your final report, I guess in 2 weeks. All right, bye-bye. I'll see you later.
Thank you.
Yeah, thank you.